Now we will talk about force of friction. Uh, Imagine that we have this block sitting on this horizontal surface. So the block is under the influence of its gravitational force, mg, pointing down, the normal force from the surface pointing up. There is a force F that's trying to pull it to the right, and we see that there's going to be a force of friction which is opposing the motion of this object with mass m. So this is basically the force of friction, or friction force is the force exerted by the surface in opposition to the motion of this object. So the surface is a rough surface, therefore it has friction. Now, we have two different cases for this force of friction. When we plot force of friction as a function of the force that we apply, first we see that the motion does not start. So the system is in equilibrium, which means the normal force balances the weight and force of friction balances the force F. So you can see that that's this linear relationship. Force of friction is equal to force F. So the slope here is equal to 1 until we reach a critical maximum value of force of friction, that is static friction maximum value, which is coefficient of static friction mu sub s multiplied by the normal force. And then the motion starts and force of friction drops to kinetic friction, which is coefficient of kinetic friction times the normal force n. So this is a rather sudden jump. Okay, so before the motion starts, we have static friction, where the force of friction is equal to minus the force applied F, that is trying to cause the motion. And when Fs reaches a critical value mu s times n, the object starts its motion, and the force of friction drops to kinetic friction force, which is mu k times n. So mu k is coefficient of kinetic friction, and n is our normal force on the block. Okay, so we can write this as force of friction is equal to the force F for F less than mu s times n, less or equal to mu s times n. It's mu k times n for F greater than mu s times n. So this is the kinetic case, this is the static case. And coefficient of kinetic friction is less than coefficient of static friction, and static friction has a maximum value mu s times n. So what causes this friction? Atomic level root of friction is the electrical interaction between atoms and molecules. Which atoms and molecules? Atoms and molecules of the surface and of the block that are in contact. Force of friction is always parallel to the surface, and it's opposing the motion, so opposite to the direction of motion. These coefficients mu k and mu s are independent of the contact area. This may sound counterintuitive because higher area would imply more contact points, but at the same time there is less pressure because the weight of the object divided by the area is less, so the pressure keeps decreasing. Therefore, these coefficients become independent of the contact area. Okay, so let's solve a few examples. A block of mass m2 on a rough, you can see there's a rough horizontal surface, is connected to a ball of mass m1 by a lightweight cord, so the tension on two sides should be the same, over a lightweight frictionless pulley as shown in the figure. A force of magnitude F at an angle theta with the horizontal is applied to the block as shown, and the block slides to the right. The coefficient of kinetic friction between the block and the surface is mu sub k. Determine the magnitude of the acceleration of the two objects. So you can see m1 is accelerating up, m2 is accelerating to the right. Okay. So we're going to start with free body diagram for m1. Now we model m1 as a point object here. Here is our y-axis, here is our x-axis. So this is y, this is x. And m1 feels its weight. So there is m1g that is pointing down, and it also feels the tension in the lightweight string, tension T, pointing up. Now from the figure, it seems that M1 is not touching this surface, so those are the only two forces acting on it. And the net force in the y direction, net force must be equal to mass m1 times its acceleration a, but the net force is tension T minus m1g, so T minus m1g must be equal to m1a. On the other hand, if I look at free body diagram for m2, I'm going to identify the forces acting on it. So M2 is going to feel a normal force from the bottom surface. So there's going to be a normal force N acting on it. There is the weight of M2, which is pointing down. So this is M2 times gravitational acceleration G. Now obviously we're applying a force F at an angle theta with respect to the horizontal surface. F at an angle theta is applied to this point. And we also have tension acting on it. Tension to the left. Because the force is causing a motion to the right, there should be a force of friction that is pointing to the left, and we have to decide if this force is kinetic or static. Because it is moving, it's kinetic friction. Fk opposes the motion and it's parallel to the surface. Okay, now net force on the y-axis must be equal to 0 because m2 is not flying away from the surface. So we have F sine theta, the y component of the force F, and the normal force adding up to the weight of the object m2g. And on the other hand, so this gives us for n, m2g minus f sine theta, and this basically tells us what the coefficient, what the kinetic friction force should be. It is the coefficient of kinetic friction mu k times the normal force. Therefore, this is mu k times m2g minus f sine theta. Okay. Now we can basically look at the force, the total force on the x-axis. Net force on the x-axis must be equal to m2 times a. And that means when I look at the x components, there is f cosine theta minus tension minus force of friction must be equal to m2 times a. So f cosine theta minus tension minus mu k times, I substitute for kinetic friction, mu k times m2g minus f sine theta, m2g minus f sine theta. This must be equal to m2 times a. And I also know that from free body diagram for m1, t minus m1g is equal to m1a. So I can write t minus m1g must be equal to m1a. So when I add these two equations, the t's will cancel, and I will find f cosine theta minus m1g minus mu k m2g plus mu k f sine theta equal to m1 plus m2a. So I can pull A from this equation. A must be equal to F parentheses cosine theta plus mu k sine theta minus G parentheses M1 plus mu k M2 multiplied by G divided by M1 plus M2. It's a rather long answer. Okay, so in this case we talked about an object that is moving under the influence of friction. So it's a system of two masses M1, M2 connected by a lightweight pulley and a lightweight string. M1 accelerates up, M2 accelerates to the right, so we have kinetic friction. First we have drawn free body diagram for M1 and we have identified the two forces acting on it, tension T that is pointing up, and there's the weight M1G. And for M2 we have talked about tension T pointing to the left, M2G, its weight, the normal force and pointing up, and of course we have friction that is at the contact between M2 and the bottom surface parallel to the surface opposing the motion. So this we have drawn modeling M2 as a point particle showing all the forces here. Net force on the y-axis is 0 because M2 is not moving on the y-axis. That gave us the normal force and Fk, which is mu k times m. The motion is on the x-axis, so we have written x component of f cosine theta minus t minus the friction force equals m2a. A is in I hat direction, and when we add these two equations we obtain A given by this long expression. Okay, now let's take a look at another example. A block of mass 3 kilograms is pushed up against the wall by a force P. So this block is touching this wall. It's pushed by a force P, making an angle theta 50 degrees with the horizontal as shown in the figure. The coefficient of static friction between the block and the wall is 0.250. Determine the possible values for the magnitude of P that allow the block to remain stationary. So the force of friction here is static, there is no motion, and we have to determine what force P we can apply in order to keep this block from falling. Describe what happens if P has a larger value and what happens if it is smaller. So let's start with free body diagram of this block. So here is our x-axis, here is our y-axis, and I'm going to look at two scenarios here for the static friction. So let's start with the first scenario. We don't know the direction of static friction. All we know is it's parallel to the surface. Okay, so here is our block modeled as a point particle. There is the force P acting on it, which is making an angle theta with the horizontal. There is the weight of the block, which is mg. There is the normal force because it's in contact with the wall. The wall exerts a normal force N on the block. And let's say that the force P is quite high, so it's trying to push this up the wall so that the coefficient, the static friction Fs, is going to point down. So this is my first scenario. Okay. Now the net force on the x-axis is 0 because the block doesn't move on the x-axis, which means P cosine theta in I hat direction and the normal force in minus I hat direction should add up to 0. Therefore, the normal force is P cosine theta. The net force on the y-axis must be equal to 0 as well, because I don't want it to move on the y-axis. The y component of P is P sine theta. There is the weight mg. I have assumed the static friction points down, so minus Fs is equal to 0. This tells me that the static friction force must be equal to P sine theta minus mg in order to maintain equilibrium. And I know that this force has a maximum value. It should be less or equal to mu s times the normal force. So the friction force that I have found, P sine theta minus mg, should be less or equal to mu s times the normal force, P cosine theta. So that tells me that P parentheses sine theta minus mu s cosine theta should be less or equal to mg. Okay. So this gives me one possible answer for P, that is P is less or equal to mg divided by sine theta minus mu s cosine theta. Now I'm going to redraw the free body diagram for the block using the second scenario, which is the scenario for which the static friction points up, which means the weight is winning over this force, so it's trying to push it, pull it down. Okay, so now we have a second scenario. In this case, again, my block is a point particle. The friction force is pointing up and the weight is pointing down. Mg is pointing down. I have the force P making an angle theta with the horizontal, and there is the normal force N pointing perpendicular to the block. Again, the net force, so this is my y-axis, this is my x-axis. Net force on the x-axis must be equal to 0 because I don't want the block to move, so that tells me P cosine theta minus N is 0 again, or the normal force is once again P cosine theta. The net force on the y-axis must be equal to 0 as well. It is P sine theta plus the force of friction minus mg equals to 0, or we can say that the static friction must be equal to mg minus P sine theta. And I know that this force must be less or equal to coefficient of static friction times the normal force. Therefore, I can write mg minus P sine theta must be less or equal to mu s times P cosine theta, and that tells me mg is less or equal to P parentheses sine theta plus mu s cosine theta. Therefore, I find that P is greater or equal to this value, mg divided by sine theta plus mu s cosine theta. So now I have considered two different scenarios. I can summarize my result. In summary, we can say that P is in a range. It's greater or equal to mg divided by sine theta plus mu s cosine theta, and it's less or equal to mg divided by sine theta minus mu s cosine theta. So when P is in this range, the object, the block, will be stationary. It won't move with respect to the wall. So let's plug in some numbers here. What is mg? What I'm calling mg here is 3 kilograms, 9.8 meters per second square gravitational acceleration. That is 29.4 newtons. Sine theta is sine 50. Sine 50 is 0.766. Mu s cosine theta is 0.25 times cosine 50, which is 0.161. So plugging in these numbers, I find that P is in this range, 31.7 newtons, and greater or equal to 31.7, less or equal to 48.6 newtons. So that is my final answer for this part. Now, I want to know what happens if P is larger or smaller than these values. So this was the answer to part A here. Now I'm going to work on part B. So what happens if P is larger than 48.6 newtons? First scenario, I have a very large force. The block starts accelerating upward and the force of friction will drop to mu k times n. So it's going to be kinetic friction, mu k times n, and it's going to point downward. So this will be corresponding to the first scenario where the static friction will be replaced by kinetic friction. P is too high, so it has a very high y component that is winning over mg and kinetic friction. The object will start accelerating upward. Now, if P is smaller than or less than 31.7 newtons, it's less than 31.7 newtons. Second scenario, the block starts accelerating downward and the force of friction drops to kinetic friction, mu k times n. However, it points upward because the motion is in the downward direction. So this would be corresponding to this scenario. The weight is too high. The P force that we're applying is not enough, and therefore the weight wins over the y component of P, and now the kinetic friction that is pointing up, and the object will start accelerating down. Okay, so this was an example for static friction. We wanted to keep this block stationary with respect to the wall by applying a force P making an angle theta with the horizontal. We have considered two scenarios. One scenario where the friction force, static friction, will point down. This was first scenario. And the second scenario where the friction force, static friction, points up. So this is second scenario. In the first scenario, I have P large enough to try to initiate this motion in the upward direction. In the second scenario, the weight is large enough trying to initiate the motion in the downward direction. So we identify the forces. One force is the normal force because the block is going to feel a force N perpendicular to its surface from the wall. It's going to feel its weight mg pointing down, so I'm assuming it has mass m, and there is the friction force acting on it. So considering these two different scenarios and taking into account the fact that the friction force is bound to be less or equal to mu s times n, where the normal force was found to be p cosine theta because it balances the y component of p to have no motion on the x-axis. We have a range of values for p. Mg divided by sine theta plus mu s cosine theta is minimum, and divided by sine theta minus mu s cosine theta is maximum. So we have numerical values given here, taking g 9.8 meters per second square, mass is 3 kilograms, theta is 50 degrees, and mu s is 0.25 as given in the problem. And we see that if p is too high, then it's going to initiate a motion in the upward direction. The static friction will become kinetic, pointing downward. If p is too low, then the weight will initiate a motion in the downward direction. Kinetic friction will be pointing up. Okay, so let's move on to one more example. Now we have two blocks here, M1 and M2, sitting on top of each other. M2 is in contact with a surface which has no friction, and M1 is in contact with M2, which has coefficient of static friction mu s. There is a force F that is applied to the right. What is the maximum value of this force for M1 and M2 to move together? Okay, so we're going to look at free body diagram for the combined system M1 plus M2. So here is our y-axis, here is our x-axis, x and y. Considering M1 plus M2 as a single particle here, I can see that there is the weight acting on it, which is the total mass M1 plus M2 times g pointing down. The horizontal surface will apply a normal force N, a contact force, and there is the force F, which is pointing to the right. Okay, the net force on the y-axis must be equal to 0 because these two masses are not flying away, so the normal force must be balancing the weight m1 plus m2g. So this is equal to 0. And the net force on the x-axis must be equal to the total mass times the common acceleration a, because I want them to move together. That means F is equal to the only force on the x-axis, m1 plus m2 times a. Now, if I look at the free body diagram for m1 alone, modeling m1 as a single particle here, I'm going to see that it has a weight m1g that's pointing down. It's going to feel a force due to m2, that's the normal force acting on m1, and it's going to feel a friction force of friction. Now, where is this force of friction pointing? Is it pointing to the right or to the left? Well, I need a force on the x-axis in order to have an acceleration a for this m1. So it's quite clear that in this case, the force of friction should be to the right, Fs. Okay, so the net force on the y-axis is equal to 0 because m1 is not flying away, which means n1 minus n1g must be equal to 0, so the normal force is m1g. The net force on the x-axis is the static friction Fs, which is responsible for its acceleration m1 times a. Because the object is not to move on m2, it has to move together with m2. So this force of friction static friction is causing this acceleration, and this acceleration is not with respect to m2, so it doesn't actually cause a motion against the surface of m2. If it did, then it would be kinetic friction we have to consider. Now, this static friction must be less or equal to the coefficient of static friction mu s times the normal force it feels n1. So we have m1 times acceleration a should be less or equal to mu s times m1 g. So these m1s will cancel, and I will find that the acceleration is less or equal to mu s times g, and the force, which I have found to be equal to m1 plus m2a, is m1 plus m2a, that is F less or equal to m1 plus m2 times a, which is a less or equal to mu s times g. So the maximum value of this force F will be m1 plus m2 times mu s times g. This is the maximum force we can apply before we lose this common motion. So the static friction will not be enough to keep m1 and m2 moving together. Okay, so this was a little bit tricky because in this case we already know the direction the static friction should have, and that is due to the fact that m1 and m2 are required to accelerate together, and there's only one force that can cause this acceleration of m1 with respect to the ground, which is the static friction force m1a. So this is less or equal to mu s times the normal force, so that gives us the maximum value of the force. Now just for exercise, let me also look at the free body diagram for m2. So for m2, modeled as a point particle here, I'm going to write its weight m2g. Now m1 will exert a force on m2. So what do you think this force is? N1 is the force exerted by m2 on m1, so m1 will exert an equal and opposite force due to the third law of Newton. So there's going to be the same force N1, which is pointing down. M2 feels this force F to the right. It also feels a normal force from the horizontal surface N2, so that is due to the interaction between this surface and M2. And now is the time to put static friction. Now you can see that static friction here is a force that develops between M1 and M2. So the force exerted by M2 on M1, the static force, is going to be to the right on M1, then it has to be to the left on M2. So this is going to be pointing to the left on M2. Okay, so the net force on the y-axis is equal to 0. This is telling us that N2 minus M2g minus N1 is equal to 0, so that the normal force N2 is N1 plus M2g. It's the force that is labeled as capital N in the N1 plus M2 diagram. It is N1 plus M2g. So note that this is the same thing as capital N. Okay. And the net force on the x-axis must be equal to m2a, which is F minus static friction. This must be equal to m2a, and the static friction force we know must be equal to m1a from the free body diagram for m1. So this must be equal to m1a. So we find that the force F must be equal to Fs plus m2a, which is m1 plus m2a. This is the same answer we have found by considering the free body diagram of the combined system. So you can see that we obtained the same result. So this checks, and everything that we have done is correct and consistent with the free body diagram of M1 plus M2. Okay, so in this case, we're looking for a maximum value of the static friction that keeps M1 and M2 moving together. So we've looked at the free body diagram of the combined system, where the forces are the normal force, the weight, and F. So we don't have to consider the friction between the two objects because the two objects are moving together as a single particle with mass M1 plus M2. And for this case, I can see that F is equal to the total mass times common acceleration. Free body diagram for M1, I have considered the weight, the normal force, the force exerted by M2 on M1. So you can note here that what I'm calling N1 here is the force exerted by M2 on M1. And there is the force of friction, static friction. Why static friction? Because it's not moving with respect to M2. Now, where does it point? Because M1 is to move together with M2 to the right, it has to point to the right. So, because it's the only force that can create this effect. And this force is equal to M1 times A, less or equal to mu s times the normal force, which is M1G. So substituting for F, M1 plus M2A, M1 plus M2A is less or equal to M1 plus M2 mu s times G. So the maximum value of F is found. And I have double checked this answer by considering M2 alone, where I have the weight, the force exerted by M1 and M2 and N1, the force exerted by the horizontal surface on M2, capital N, the force F, and then I need the static friction. The static friction develops between M1 and M2. If it is acting to the right on M1, it has to be acting to the left on M2, opposite in direction, equal in magnitude, Newton's third law. So I find that F must be equal to M1 plus M2A using this free body diagram, consistent with my previous answer. Okay, let's move on to another example. Again, we have M1 and M2. There is friction between M1 and M2 on the y-axis at the surface, side surface of M2. A force F is pushing M1 against M2. And what is the minimum force required to have M1 and M2 move together? Now, I'm going to draw a free body diagram for the combined system M1 and M2. So here is y-axis, here is x-axis. M1 plus M2 modeled as a particle here feels a force F to the right. There is the weight M1 plus M2G, which is pointing down. Now, if I don't want these two guys to slide down against M2, then I'm going to consider the friction pointing up, but that's when we consider M1 alone. For M1 plus M2, we don't consider friction because it's a combined system moving together. We only have the normal force that is exerted by the bottom surface here. The bottom surface exerts a normal force to this combined system. So that is the normal force N. The net force on the y-axis must be equal to 0, and 1 plus m2 is not moving, so n minus m1 plus m2g is equal to 0. Therefore, the normal force is the total weight, m1 plus m2g, but pointing in the opposite direction, pointing up. Net force in x must be equal to the total mass m1 plus m2 times their common acceleration on the x-axis. The force applied to the right is F, so F is equal to m1 plus m2a again. Now I consider m1 alone. So m1 is modeled as a particle. It has a weight pointing down, which is m1g. It feels this force F pointing to the right. It feels a normal force from m2, so this I can call force exerted by m2 on m1, the normal force. And where do I put static friction? Because I don't want it to slide down, the static friction must be opposing the weight. The net force on the y-axis must be equal to 0. Therefore, static friction minus m1g should be equal to 0, so that the static friction is m1g. The net force on the x-axis must be equal to m1a, because m1 is to move together with m2 with the common acceleration a. So it is F minus force exerted by m2 on m1 equals to m1a, and the force F is m1 plus m2a, and if I subtract from this m1a, I find the contact force Fm2 m1. So m1a's will cancel, so I see that the force exerted by m2 on m1 must be equal to m2a. Then the friction force, static friction, should be less or equal to μs times the normal force, which is μs times the force exerted by m2 on m1. So because I know that the static force friction is m1g, m1g must be less or equal to μs times Fm2 m1, which is m2 times a. Okay, so we can write basically for acceleration. You can see here acceleration is greater or equal to m1g divided by μs times m2. So this allows me to write the force, which is m1 plus m2 times a, to be greater or equal to m1 plus m2 multiplied with m1g divided by μs m2. So this gives me the final answer, basically the minimum force F I can have for this these two objects to move together is this force is has a minimum value m1 times m1 plus m2 g divided by μs times m2. Okay, now just to double check, I want to draw the free body diagram for m2 as well. So m2 is a single point, modeled as a single point. It has a weight m2g pointing down. It's going to feel a normal force from the bottom surface n2 pointing up. It feels the force due to m1, force exerted by m1 on m2 pointing to the right. And where is the static friction pointing? Because it's pointing up on m1, it has to be pointing down on m2. So this is going to point down. So let's redraw this. It's going to point down on M2. The net force on the x-axis must be equal to M2 times A. So the net force on the x-axis is force exerted by M1 on M2. That is equal to M2 times A. The net force on the y-axis must be equal to 0. Normal force N2 minus M2G minus the static friction is equal to 0. The static friction is M1G that was found from the free body diagram for M1. So this is basically going to tell us N2 minus M1G minus M2G equals to 0. So the normal force N2 must be equal to M1 plus M2G. Okay, so another example for static friction between M1 and M2, where M1 is leaning against M2, we're applying a constant horizontal force F, and we want to know its minimum value so that M1 will not slide against M2. They will move together with a common acceleration A to the right. There is no friction with the bottom surface. So what I have done is I have considered the combined system M1 plus M2. There's the weight, the normal force, and F. Those are the only three forces acting on the combined system, which tells me that F is equal to M1 plus M2 times common acceleration A. Then I draw the free body diagram for M1, where I see the force F, M1G, and force exerted by M2 on M1, and the static friction, which is pointing up in order to have M1 not slide down. And this tells me that the static friction must be equal to M1G, which is less or equal to μs times the normal force, where the normal force is the force exerted by M2 on M1. The net force on the x-axis is equal to M1A, so that tells me force exerted by M2 on M1 is M2A, so I can find from the condition that the static friction should be less or equal to μs times the normal force, M1G should be less or equal to μs times M2A, which implies acceleration has a minimum value M1G over μs M2, and force has a minimum value M1 plus M2 times M1G over μs M2. I double checked this with free body diagram for M2, where I note that the force exerted by M1 and M2 is equal in magnitude and opposite in direction to the force exerted by M2 on M1, and also the force exerted by M2 on M1 due to friction was pointing up. Now acting on M2 due to M1 is pointing down, Newton's third law. So using this equation, I find that the normal force for acting on M2 is M1 plus M2G, which is consistent with our combined system scenario. Okay, so let's take a look at one more example. We have a system of capital M, M1, M2. M1 and M2 are to move together. There is a friction μ1 between capital M and M1. There is a friction M2, μ2, coefficient of kinetic friction μ2 between M2 and capital M. There is a force F applied to the right. There is no friction with the bottom surface. Okay, so I start with the free body diagram for the combined system M1 plus M2 plus M. So this is my x-axis, this is my y-axis, and here is the combined system, feeling the force F to the right, the total weight pointing down. So it is capital M plus M1 plus M2G, and there is the normal force from the bottom surface pointing up. The net force on the y-axis must be equal to 0 because they're not moving on the y-axis. So normal force minus capital M plus M1 plus M2G is equal to 0. the net force on the x-axis is equal to the total mass m plus m1 plus m2 times the common acceleration a, where the net force on the x-axis is F, so this is capital M plus M1 plus M2 times A. Okay, let's work on M1 now. Free body diagram for M1. Now for M1, I see that I have the weight pointing down, M1G. There is the tension pointing up, tension in the lightweight string pointing up. There is the force exerted by capital M on M1 because they are in contact. And now I have to put a static friction. I'm going to consider two scenarios. The static friction is pointing up or the static friction is pointing down. Okay? Now, this is one scenario, static friction acting on M1 and static friction acting on M1 pointing up. Okay. Now, the net force on the x-axis must be equal to M1 times the common acceleration A. So force exerted by capital M on M1 is equal to M1 times A. The net force on the y-axis must be equal to 0. So the tension plus, let's consider the first scenario here, Fs1 pointing up minus M1G is equal to 0. So we will have the force of friction Fs1 is equal to M1G minus tension, which is less or equal to mu s times the normal force, so it is mu1 times m1a, because the normal force we have found to be m1a. Or we can have the second scenario, tension is pointing up, static friction is pointing down, tension minus Fs1 minus m1g is equal to 0, and we would find that the static friction Fs1 is equal to T minus m1g, which is less or equal to the static friction coefficient mu1 times m1a. Okay. Now, if I go to the free body diagram for M2, I have the weight of M2 pointing down, M2G. It feels the normal force N2 due to capital M, so N2 is pointing up. It's going to feel a tension to the right, T to the right. Now I have to consider two scenarios for static friction. Now, if this system is trying to move down, the static friction Fs1 was pointing up on M1 and it would be pointing to the left on M2. So the blue scenario is basically static friction points to the left, and if the system is trying to move up, then we would have static friction pointing down on M1 and pointing to the right on M2. So these two scenarios are coupled. Okay, so the net force on the y-axis is equal to 0. So that means the normal force must be balancing M2G. And the net force on the x-axis is equal to M2 times the common acceleration A. So it is tension minus Fs2 or plus Fs2. So tension minus Fs2 is M2A, or tension plus Fs2, the red scenario, is equal to M2A. So this tells us that tension minus Fs2 or tension minus M2A, which is Fs2, is less or equal to the coefficient of static friction mu2 times M2G, because the normal force is M2G, mu s times n. Or we see that Fs2 is M2A minus tension, that is less or equal to mu2 times M2G. So we have considered two possible scenarios here. Now let me move on with two different scenarios. So let's work with FS scenario where I have the static friction pointing up on M1, pointing to the left on M2. So in this scenario, I have M1G minus T is less or equal to mu1 M1A. So M1G minus T is less or equal to mu1 M1A. And here, the same scenario from free body diagram for M2 gives T minus M2A is less or equal to mu2 M2G, or T minus mu2 M2G is less or equal to M2A. So T minus mu2 M2G is less or equal to M2A. That's obtained from this inequality. So if I add these two, let's add these two, I will find the tensions will cancel. M1 minus mu2 M2 parentheses multiplied with G divided by M2 plus mu1 M1 is less or equal to A. So this is one possibility. Now let's work on the other scenario, the red scenario. For this one, I'm going to have T minus M1G is less or equal to mu1 M1A, and M2A minus T is less or equal to mu2 M2G. You can see that from these equations, Fs1 is equal to T minus M1G less or equal to mu1 M1A. That's the first inequality. The second one, M2A minus T is less or equal to mu2 M2G, or M2A, yes, so this is the same inequality copied here. So if I add these two inequalities, so let's do this here, the tensions will cancel, and I will find that M2A minus M1G is less or equal to mu1 M1A plus mu2 M2G. So A parentheses M2 minus mu1 M1 is less or equal to G parentheses M1 plus mu2 M2. So that means the acceleration is less or equal to M1 plus mu2 M2 times G divided by M2 minus mu1 M1. Now I remind you that the force F is equal to capital M plus M1 plus M2 times A. So this gives me the range of values for the force. So the force F is capital M plus M1 plus M2 times M1 minus mu2 M2 G divided by M2 plus mu1 M1, that's the minimum value of F, less or equal to M plus M1 plus M2, M1 plus mu2 M2 G divided by M2 minus mu1 M1. So these are the range of F values for which we would keep this system moving together. Well, the question was, what is F minimum and what is F maximum? Well, what is F minimum? We can read it here. F minimum is M plus M1 plus M2, M1 minus mu2 M2 G divided by M2 plus mu1 M1. This is the minimum value. And the maximum value would be F max equals capital M plus M1 plus M2 times M1 plus mu2 M2 G divided by mu2 minus, M2 minus mu1 M1. Okay, so as you can see here, we have to consider all possibilities for static friction. Static friction can be pointing up or down, or to the right or to the left. It has to be parallel to the surface, opposing the motion. If the motion is to the right, the M1 is going down, M2 is going to the right, it will act to the left on M2 in the upward direction for M1. If M2 is going to the left, the force of friction will be pointing to the right, and M1 is going up, the force of friction will be pointing down. So that, or that is the tendency rather, then the static friction directions would be given by the red scenario. So by considering these two different scenarios, we find a range of F values, and that allows us to determine minimum and maximum allowed values in order to keep capital M, M1 and M2